Hello everyone, welcome to this online class, Road Subgrade and Pavement Engineering. This class is offered by the School of Highway at Chang'an University. My name is Yang Xu. I will take charge of the section Subgrade Soils and Pavement Materials. Now let's go to the first part of my section, the subgrade soils. Here is the content of this section. It is composed of three parts. The first part, the subgrade soil classification. Part 2, subgrade moisture evaluation and conditions. And part 3, subgrade bearing capacity. Now let's go to the first part. In our daily life, when we talk about soils, I think probably in our mind we may have this picture. That is the soils for the plants and for the agriculture. However, in civil engineering, when we talk about soils, we may talk about a lot more. For example, we may have gravels like this. We may also have chips like this. We may have coarse sand like this. We may also have fine sand. So, if we have such a broad definition of soils in civil engineering, we may need a classification system to categorize them. Generally, we may have three types of classification systems for different soils. Here are them. We take a look. The first one we call Unified Soil Classification System, USCS, and the AASHTO Soil Classification System, and also the Highway Soil Engineering Testing Specification, that's from China. Let's take a look at them one by one. The first one, USCS. So generally, USCS is a classification system in engineering and geology. It is to describe the texture and grain size of a soil. And it is usually represented by two-letter symbols. So what are the two letters? For example, the first letter, it is usually denoted by, for example, G, S, M, C, and O. Respectively, we say them gravel, sand, silt, clay, or organics. The second letter, it is usually denoted by the gradation and the plasticity. For example, they can be represented by P, W, H, and L. And this symbol chart gives us a more clear description of the classification. Generally, it can be classified into three types. For example, the coarse grained, the fine grained, and highly organic. And we can also see a lot of them are represented by two-letter symbols. For example, if we have SP, means that poorly graded sand. This is the second one, the AASHTO. Generally, the AASHTO classification system categorizes the soils into two big categories. First is the granular materials. The second one is the silt and clay materials. Generally, they are also denoted by A1, A2, A3 until A7. And A1 to A3, they fall into the category of granular materials. And of course, generally they have a higher size. And in terms of the performance for the subgrade soils, the granular materials, they are excellent to good. However, in comparison, the silt clay materials, they are only fair to poor. And in terms of the China's specification, actually China's classification system is a modified system based on the USCS. And from this chart, we can also see clearly it can be mainly categorized into four classes: the over coarse grained, the coarse grained, the fine grained, and the special soils. Generally, the over coarse sized, it has more than 15% particles larger than 60 mm. And the coarse, it has less than 15 particles larger than 60 mm. And meanwhile, it has more than 50% particles larger than 75 microns or 0.075 mm. And for the fine ones, we can say that it has more than 50% larger than 75 microns. Here is that we can also see that the China's classification system the symbols can also be represented by 2-letter or 3-letter symbols we can see here. For example, if we have SW means well-graded sand. And we can see from this table that we have several symbols. For example, the symbol of components, symbol of gradation, symbol of liquid limit, and a symbol of special soils. And for different types of soils, they may have different engineering properties, especially when we utilize them in the highway engineering. So we need some information, especially the engineering property information. So what are the properties of different soils? For example, if we have over-coarse or coarse-grained soils, generally they are stable with high strength and permeable, and they are independent with construction seasons. And in comparison, for the fine-grained soils, generally they are cohesive, non-permeable, and dependent with construction seasons. And I also want to highlight that for some special soils, if they are utilized for the subgrade filling in highway, we may need some special treatments for them. Now let's go to the second part, the subgrade moisture conditions and the evaluation. We all know that the moisture condition is an important factor affecting the subgrade soil performance or properties. So we need to understand the moisture conditions very clearly so that we can estimate their performance. So how to evaluate the subgrade moisture condition? Before that, I want to introduce a terminology called equilibrium moisture. What is that? So we know during the service life, subgrade moisture varies from time to time because of the underground water and the surface water. However, this variation rate may become stable after a period of while, for example, 2 or 3 years. Then the moisture under this condition is called the equilibrium moisture. And under the equilibrium moisture, we can estimate the capillary effect of the underground water. So if we compare the subgrade walk down and the capillary effect surface, so we can categorize the moisture condition into 3 classes: the dry, the moist, and the wet, like here. And these slides give us a more clear description of how to classify them. For example, the wet condition, if the capillary wetting surface is over the subgrade walk down, it is called the wet condition. If it is within the subgrade walking down, it is the moist condition. However, if it is under the subgrade walking down, it is the dry condition. Now it's part 3, subgrade bearing capacity. We know that subgrade is the foundation of a highway. So the bearing capacity of the subgrade will definitely affect the stability, especially the structural stability of the highway structure. So we need to evaluate the subgrade bearing capacity. Then, how to evaluate it? Or do we have any criteria to say, oh, this subgrade is stable and that one is not that stable? We have generally 3 different indexes. They are resilient modulus, reaction stiffness, and the California bearing ratio. What are they? Let's take a look one by one. The first, resilient modulus. We know that for many materials, for example, the metal concrete, we may have elastic modulus, but for soil, we don't have elastic modulus. We may have an estimate of elastic modulus. That is resilient modulus. Then, how to get the resilient modulus? For example, if we have the road bed, and then we apply a cyclic loading, and then we can see the deformation and the load. Or eventually we can also see the stress and the strain level. For example, on this graph, you can see that at the beginning we have a larger deformation, and this deformation becomes to be smaller and smaller with the increase of the loading cycles. And for the resilient modulus, we can calculate it by the difference of the stress divided by difference of strain, or we can say that MR equals to delta sigma divided by the delta epsilon, like this equation on the graph here. Generally, we can say that if a higher resilient modulus means a more stable soil. And for the resilient modulus, we can test them both in the field and in the lab. For example, on this slide, we show the pictures for the field test and the lab test. So that is the resilient modulus. Now let's take a look at the second one, the reaction stiffness. Reaction stiffness, what is that? Generally, we can say that the subgrade is simulated with a set of separate springs. We call this a Winkler model. Actually, Winkler model is very famous in pavement engineering. This picture gives us a very direct illustration of the Winkler model. It is composed of several springs, and those neighboring springs, they has no effect on each other. And the reaction stiffness is a plate stress divided by the total displacement. And be mindful here, the total displacement means that both elastic and plastic. And then the reaction stiffness, if we denote it with K, equals P divided by W. And for this test, we can see that it is performed without unloading. We just load it, and we check the deformation, we check the load. There's no unloading, so this is different from the resilient modulus. So the last one is a California bearing ratio. This is a very, very important index or parameter in the soil testing. Let's take a look. What is that? The CBR is the ratio between the pressure of the testing specimen, P, and the standard MACDAM at the penetration displacement of 1 inch or 2 inches. And the CBR equals P divided by PS times 100%. And how to understand this? For example, if we have a standard MACDAM and we apply a penetration test, we apply a load, then we get a deformation of 1 inch or 2 inches. And we record the stress level, that is standard stress. And if we have an unknown soil, we do the same testing, and we also get the deformation about 1 inch or 2 inches. And we record the pressure, we call it P, and then we get the ratio between the P and the PS, and we get the California bearing ratio. And here, of course, if you think about it, a higher CBR indicates a more stable soil, right? And the CBR value can be obtained by a penetration test, both in lab and in the field, like the graphs here, that is the field test and the lab test. Okay, now I think it's a summary of this mini class. And in this class, we introduced 3 parts. The first is about the subgrade soil classification system. We introduced 3 different classification systems, the USCS, the ASHTO one, and the Chinese one. The second part is the subgrade moisture conditions and evaluation. We provided a criteria to determine the moisture conditions. And the part 3, subgrade bearing capacity. And we introduced 3 different parameters to determine the bearing capacity. They are the resilient modulus, the reaction stiffness, and the California bearing ratio. I think that's it for this class. And thanks for your attention. We'll meet next mini class. Thank you.